Previously, we have learned about monohybrid inheritance, and Mendel has shown to us that the phenotypic ratio in monohybrid inheritance would be 3 to 1. 3 dominant trait, or 75% of dominant trait, to 1 to 25%, or to 1/4 of recessive trait. But he doesn't stop here. He continues to explore on the inheritance involving two types of characteristics, and this is what we call the dihybrid inheritance. In dihybrid inheritance, Mendel actually tried to cross the pea plants from two pure breeding characteristics. One is the tall. One is a plant with tall and round seed. The other one is a pure breeding recessive plant. As you can see here, it's short and it has ringed seed. So let the tall plant, let the allele that controls the tall trait to be capital T. The allele for short trait to be small t. Allele for round seeds, capital R, and allele for ringed seed, which is the recessive trait, as small r. So definitely, since they are both pure breeding plant, so that means to say that the genotype would be big T, and big R. For short and ringed plant, since it is a pure breeding short and ringed a plant with ringed seed, so the genotype must be small t, small r. So during the formation of gamete, as suggested in Mendel's first law just now, the law of segregation, the pair of allele must separate. Gamete will only get either member of that pair of alleles. So in this case, we see that the gamete produced by the tall and round seed plant will be capital T and capital R. Whereas for short and ringed seed plant, there is only one possible gamete, which is small t and small r. During random fertilization, as predicted in Mendel's first law, the F1 generation will all be having this type of genotype, making them having the characteristic as a tall plant with round seed. But what happened to all the recessive traits? What happens to the round seeds, the ringed seed and the short plant? Where do they go? So to find out, Mendel actually tried to do the self-pollination between F1 generation. So right now he tried to cross the F1 generation with another F1 generation with the same genotype. So guess, in this case, what are the 4 possible gametes that will form? So big T and small t will separate as stated by the law of segregation, same as big R and small r. But the big T can combine with big R to form a gamete. Big T can also combine with small r to form another gamete. Small t can also form a gamete with big R and with small r. So this gives rise to the 4 possibility of the gametes. Now, so how do we predict the F2 generation? Are we going to do it this way? Yes, you can. So the first combination, will give you the big T, and big R. The second combination here will give you the big T, big R, and small r. And of course, during random fertilization, it has the equal chance to fuse with another gamete. to give rise to the second filial generation with this genotype. So we may want to complete it. And you will discover that doing so is actually very troublesome. Now, so to save our time on random fertilization, that's why scientists introduce another method known as Punnett square. So in Punnett square, what you need to do is to list down the gametes produced by the male plant and the female plant. So during random fertilization, the gamete from the male plant can fertilize with another gamete from the female plant, giving rise to this F2 generation. It has also the same chance for this gamete to fuse with this gamete, giving rise to this F2 generation. So when you complete the table, then you will get all the 16 possibility of combination. Now let's look at the phenotype of this F2 generation. Big T, and big R. So the phenotype of this plant, of this F2 generation, will be tall and round. Okay, so I'm going to count it using the matchstick method. I get 1 here. Big T, big R, small r. So again, I get a tall and round plant, round seed plant. Okay, now let's see the fourth one. Big T, big R, small r. This is a heterozygous plant. Again, since big T is dominant over small t, big R is dominant over small r. So again, this F2 will be tall and round. Let's check this. This is also tall and round. This is tall and round. Now, please place attention to this. This is not a conventional way of writing phenotype. Remember, we always write the dominant allele before recessive allele. So we should write this way. So this is again again tall and round. This is also tall and round, and we have also tall and round here. Now let me repeat again. It should be written this way: tall and round, tall and round. So basically I have 9 out of 16 of them, okay, to be tall and round seed. And then what about this one? Big T, small r. It will be tall and wrinkled. Alright, so this one is also tall and wrinkled. Now tall and wrinkled, let's see. Tall and wrinkled. So out of 16, I get 3 of them, okay, to be tall and having wrinkled seed. What about this? This is small t, big R. So it's short, however it has the round seed. I have 1 of it and another 2 for it. So the last combination would be small t, small r. So if you were asked the phenotypic ratio in dihybrid inheritance, then it would be 9:3:3:1. Okay, will you be asked the genotypic ratio in dihybrid inheritance? The answer is no, because if you were to list down the genotypic ratio of in dihybrid inheritance, then it will be extremely long. Now, so you have 1 of it. 1:2:2 is to 2 is to 1 is to 2 is to 2 is to 1 again is to 2 is to 1. So I guess this type of questions will most likely not come out in examination. So from the dihybrid inheritance, he proposed the second law, which is the law of independent assortment. Assortment means combination, so they can combine randomly. Let's look into this second law. During the gamete formation, each member of the first pair of allele may combine randomly with either members of another pair of allele. It can be shown using this diagram. Now we can see two pairs of homologous chromosomes. These two are the homologous chromosome. These two are also the homologous chromosome. So during metaphase 1, they can either arrange themselves this way or this way. If the homologous chromosomes are arranged this way, then during anaphase 1 or anaphase 2, this is how they speak. Can you see that? So as a result, the big T now pair with big R, and in another gamete, you have small t pairs with small r. However, there is equal chance for the homologous chromosome to arrange themselves this way. So if they arrange themselves at the metaphase plate this way, then during anaphase 1 or anaphase 2, they are going to separate this way. You get big R and small r in one gamete, and small t with big R in another gamete. So this is explained by the Mendel second law, which is known as the law of independent because they can pair freely, randomly with another allele. Okay, thank you. Okay, so let me summarize quickly on what we have done so far. In monohybrid inheritance, the phenotypic ratio would be 3:1. 3 dominant trait and 1 recessive trait. In dihybrid inheritance, the phenotypic ratio is 9:3:3:1. 9 out of 16 are having the dominant traits only. 1 out of 16 are having the recessive traits only. While this 3 and the other 3 are just a combination of dominant trait and recessive trait. And when you were asked to draw a schematic diagram on inheritance, remember to start it from parents, and the parents will have to cross, to get the F1 generation. And then in between parent and F1 generation, you have this gamete. Remember also to label the phenotype and the genotype of the parental generation, as well as the phenotype and genotype of the F1 generation. And then start to put in the genotype of the parents by reading the text carefully. Normally, we will be given information about the genotype of this, about the phenotype of the parents, and from the phenotype, we can guess the genotype of the parents. Okay, so please practice yourself on how to draw a schematic diagram on inheritance, as it will be tested in examination. So see you, all the best.